Hello everyone. Let's continue with logic and proofs. This week we are going to finish the topic related to logic and proofs, but they will be useful for us anyway for other topics. You may mention that why we need logic and proofs as engineers, because you guys want to see the solution just step by step, like the problems that usually solve in engineering courses. Time to time it can be frustrating for you, and I understand it, because these things are usually fun for pure mathematicians, and they love to see how things are happening behind the curtain. But for engineers, you would love to see the applications. You need to see how we can solve problems related to that. So I understand your frustration, and as I promised before, in weekly assignments you will see mostly applications, not theories. We are not going to prove new things, for example, inside weekly assignments, and you will see. Sorry. So let's continue with nested quantifiers. So we already introduced you about the quantifiers. So for all x, you already know what it means. But let's see when we are dealing with nested quantifiers for all x's and for all y at the same time, and whether the order matters or not. We will keep talking about it, and I will show you examples related to that. But what does it mean? Here we have an expression in front of it, and this function, as we can call, is bounded, not free. It means that quantifiers are actually bounded to this expression. Now, for the next one, we see there exists instead of for all. So what are the differences? For example, here we say for all x's and y, this equation holds. It means that the order of addition doesn't matter in real numbers. If I interchange their places, like for example, x plus y or y plus x, the equation holds, right? And we define it on real numbers. Usually as engineers, you guys deal with real numbers, and sometimes in specific cases complex numbers, and that's all. But in pure mathematics, we should define different fields, and based on the fields, this kind of things is not clear as it shows here. For example, for you it's pretty obvious that this is okay, but it depends really in which field we are defining it. Let me see if we have a question or there's a technical problem. Just let me check. Is it the same for others? Everyone can hear me? Okay, so Serhan, please restart. Great. Okay, so please let Serhan to restart and come back. So let's continue. And please, if you have any questions, please wait until the last slide, then I will take your questions, because as you can see, it takes time to bring back the slides, and I check the window for you. All right, for all x's and there is a y, at least there is a y, maybe there are more than one, then we have such a case. And whenever there is only one unique number for that, we use another notation, which maybe we will talk later. But let's see what it means. It means that for all x's that you can imagine in real numbers, for example, like if we have 1, if we have 100, if we have -2, if we have -2.12, in any case, you will at least find the y that this equation holds. For example, if you have 2, then you have -2 to make it 0. See? So if you have pi number, you have minus pi, then you will make it 0. And that's how it can be defined. As you can see, nested quantifiers can be very useful in order to define several mathematical reasoning. And for example, for this one, you can see even implication is used, and we have nested quantifiers for that as well. So for all x's and y, we have such a condition. Now let's see how order matters, because sometimes if you change the order, that could totally change the meaning. So if there is a question, please wait until the final slide. Otherwise, if there is a technical problem, again, please send a message so that I understand I should check the chat room. Okay, so here you can see for the first sentence, we have there exists y, but for all x's, we have such expression. So there is a real number y such that for every real number, we have such a term. But this is false. If I change the order, like for all x's, there is a y that makes it happen, this is true. Can you see the difference? Like, for example, I define 2 as x, but for all y, can I make 2 0? No, only for -2, I can make it 0. So you see, it's very important that where you put the order, and for this case, I use for all before there exists, so that this one is meaningful. It depends on your function, that's what you define here, and we should be careful about the order of quantifiers. So let's take a look at this one. For example, for all x's and for all y, this is our function, so it holds for this function. It's nice to ask ourselves when this is true and when this is false. And as you can see, for showing that this is true, for all x's and y's, I should show that this is true. And I show them by 2 components. It means that we are just going through them pairwise. If I had 3 elements, if I had 3 components, then 3 by 3 at the same time for all x, y, and z, it should work. But when this is false, it can be proven by using counterexample. I will show you in proofs that how we can do it. So to show that this term is false, it's very easy, because if you find just one example that this function doesn't hold, then that's it. You can say that this term is false. But when you use, for example, there exists, things can change. Or even when you use 2 there exists, and you see to show that it is false or true, they are totally replaced. So it's much easier to, for example, show that one is true or one false and other is different. So please go through this table. It gives you some light that what are the meanings of nested quantifiers and how I can say, for example, this is true or this is false. And what about negation of quantifiers? We already showed that for different compound propositional logic, but let's see what happens to quantifiers. Like, let's say I apply this negation to this term. So for all x's, there exists y such that x, y is equal to 1. This one is equivalent. So you see, for all changes to there exists. So whenever you apply negation to for all, it changes to there exists. And whenever you apply it to there exists, it will changes for all. It's pretty easy. You can simply negate this one with there exists and vice versa. What about the expression? The expression should be negated as well. By the way, sometimes when I uploaded the slides, you can see some errors in them. But when I talk about them in the lecture, I already fixed the problem. So, for example, this one maybe in the lectures that you have already seen is different. That's why it's very important for you guys to keep watching the lectures and don't depend on the just reading the slides, because reading the slides are not helpful for you if you don't watch the videos. That's why I suggest you to keep watching the videos, and whatever we say in videos, that's the most important thing. Unfortunately, for discrete mathematics, we don't have that much confliction. Like, whatever I say is based on the book, so we don't have any conflict with the book. For example, in a course like statistics, maybe I have some taste in solving some problems, and the statistic is not that solid like mathematics. But fortunately for our case, this is not, but then it's okay. So you see, for negation, it's easy. You just change the quantifiers like this and just change the equation from equality to not equal. If it was greater than, then it will be less than and equal, for example, for this scenario. Now we need to know about some important terms in rules of inference. And through that, you will be introduced how what we mean by rules of inference. And this is the base of proving theorems, and we need that. So here I listed some words for you with their definition, but let's see what the book exactly mentioned about them. An argument in propositional logic is a sequence of propositions. So argument is the sequence of proposition, nothing different from them. It's just a collection of them. All but the final proposition in the argument are called premises, and the final proposition is called the conclusion. Okay, so inside the argument, we have premises, so series of premises, sequence of premises, and at the end, the last one, which is our conclusion, we call it conclusion. So an argument, which is the sequence of these propositions, which we already know from previous lectures, is valid if truth of all its premises implies that the conclusion is true. So you see, we have collection of these premises, and if all of them together form an implication to show that the conclusion is correct, then we call that argument valid. And we can also, after argument, define argument form, which is in propositional logic is a sequence of compound propositions involving propositional variables. An argument form is valid no matter which particular propositions are substituted for the propositional variables in its premise. So what is important in argument form is that we should know about different equivalences, and I will show you one example related to that. If this is the case, that we can use arguments as a segment, the whole of them as a segment, as argument form. And this is very useful in order to prove our theorems. Take a look at this simple example. For example, if I ask you whether this argument is valid or not. So for this one, we know that if P implies Q and P is true, when I just say P, it means that if either true or false, and you can show it in the table of truth. We are just tackling it component-wise. What does this notation mean? It means that therefore. So in conclusion, finally, we say therefore this is correct, logically correct. So by changing the truth and false values of the table, it can be implied that Q is true or false. So as you can see, instead of having the whole truth table, mathematicians use such notations. And in that case, argument, because argument, when we say it in computer science, maybe it just means the input of a function, you know? So when we say argument in discrete mathematics specifically here, we mean that the series of these premises. So these are the premises, and this is the conclusion. And you see, I don't need a table of truth. Now, logically, I can prove such things. And later in theorems, you will see how it's done. So if this is, we asking this is valid, yes, this is valid, because if these ones hold, then for sure we can include that if P is true, Q is true. If this is false, so this one is false. So it holds for that. Now, let's take a look at rules of inference for propositional logic. We continue with that with an example. So the tautology here, what do we mean by tautology? Let's remind ourselves. It means that if you have the table, truth table for this expression, all the time you will receive true in the final column, right? So if you consider this one as a compound proposition, then in the last column of your table of truth, you will see it will always lead to truth at the end. So we call it tautology. So this tautology is the basis of the rule inference called modus ponens. This is a Latino word, so I just talk with the Latino pronunciation. And the law of detachment. We can also call it that. So this one is famous, and they use it a lot. A conjunction between P and its implication to Q, it implies the whole thing to Q. So you may ask me, how can I see it directly? Yeah, you should use a truth table or some arguments in order to show that. So mathematicians, usually they use it a lot so that they remember instantly. But for you guys, this is totally natural. Don't be disappointed, for example, if you don't remember these things. We don't expect you to just remember these things right away. I don't expect you to prove new theorems, for example, because as I mentioned, this is good for pure mathematicians, because assume that you know, then if you don't use it, what's the goal of that? But I'm focusing on the things that you will use in computer science. So this tautology leads to the following valid argument form, which we have already seen in our initial discussion. Yeah, we mentioned it about it, and also we mentioned that this one, this symbol, means therefore, or it implies, or thus, something like that. In conclusion, usually we use this. So the previous one, we use P after implication. Now this time is different. Okay, first we have this proposition, then we have implication, and again by using this tautology, we can prove this is true. So you see, not always we need table of truth because it's very primitive, but we need to know what is the table of truth and how it works, and I will give you one assignment related to that next week for sure. There are many rules of inference, and you can see some famous ones. They have even names. You see, for example, this one, they use it a lot. I'm sure you saw it before, like P implies Q and Q implies R. So can we say P implies R? Yeah, this is true. So this one is very famous. Most probably you are familiar with that even from high school. So all of them have names, and how can I prove this is a tautology? Whenever they ask you, is it a tautology? How can I prove it? Table of truth, and the last column is full of truth values. We don't have any false. There is one application of that in computer science. They use it a lot in programming, which is called resolution. Take a look at this one. So we have a conjunction between these two propositions. Both of them are disjunction. One of them has the same proposition, but one of them has negation before it, but the other one has a different variable. And at the end, look at this one. It implies QR. It means that we don't have P proposition in the result of this implication. See? So this one is very famous. And how can we prove it? Again, using arguments or table of truth. And let's take a look at these terms, like where this disjunction is called resolvent. That's what they call it. To construct proofs in their propositional logic using resolution as the only rule of inference, the hypothesis and the conclusion must be expressed as clauses. What is a clause? Where a clause is the disjunction of variables or negations of these variables. Exactly. Okay. So each one of them are clause. And you see, we just used P and negation of P in order to finally reach this disjunction, and we should use conjunction between them. The application of this is vast in computer science. Many programs, they use such a logic. It solves many problems. Now, take a look at this example, like how we can, for example, show these two are equivalent. By the way, how can we show it? For example, assume that we can use table of truth. It means that the last column of this compound proposition should lead exactly to the same t and false values, which are the same with this one. The last column of this propositional compound propositional. So if you ask me what's the difference between tautology and equivalence, because are very similar, right? Sometimes when you hear about tautology, you mix it up with equivalence. There's a vast difference because for tautology, we use all the last column to be truth, but it's not the case for equivalence. If maybe the whole thing is false here, the whole thing for compound propositions here should be false as well. We don't have such a case in tautology, okay? But if the tautology holds, of course, we can find equivalent compound propositions from that. Anyway, I don't want to go through details about it. You will see it in example. It makes sense for you much better. So based on such rules, and for example, the rules that we know from before, like Morgan's law, we can come up even with new arguments. And so it's like we are building a big apartment using small blocks. And these blocks, all of them are based on logic. And that's why we need to know these things, that what's happening behind the curtain, so that we would appreciate it in the applications. So you may ask me again why we need such things as computer engineers to know what's happening behind the curtain, because, for example, I don't care. I just want to see the application. First of all, I should also mention that these are inside your syllabus. So I cannot change some of the things inside the course syllabus. They already decided. So I'm stuck with this chapter, and I should explain all about the details. But all I can do, as I said, is to focus on application when we are dealing with examples. We will see. Let's see this example. Like, show that premises this compound proposition and just this implication. Show that these two together imply the conclusion, this disjunction, the disjunction S. So in order to solve it, then we can rewrite premises like two clauses, like the one that we mentioned before. I heard that there's a message. Let me finish. It is about to be finished, and I will receive your questions. But if there's a technical problem, again, please type again and let me know. So we can rewrite the premises, these two, as actually this compound proposition as two clauses, as we mentioned before. Like we had, you see, we had clauses now. So in that case, instead of just having one single compound proposition, I can show them by these two disjunction. So it's like applying this disjunction one by one to these two propositions. And we can also replace R implies S by this equivalent clause. How do I know that these two are equivalent? For example, this is one application of what we mentioned here. You see? So we should know about all the things happened before in order to be able to build our building. That's how it works. We should start from the first little components in logic in order to come up with such equivalence, and one by one we can create it. You may say, okay, when I'm trying to solve this problem, I don't even remember, for example, about the previous ones, and this is a frustrating task for me. And you're right, even for pure mathematicians, time to time it can be challenging. If they haven't seen one proof of a theorem, it's very challenging for them to prove it again. So it's totally natural, and we don't expect you to solve such examples. But you should know, as they are mentioned in the syllabus of the course, as I mentioned, it's my job to introduce all of them to you. And we will, what I expect you guys to do, just try to understand the topics as much as possible. That's it for the first 2 weeks. All right, I keep talking about it because you're asking questions about that. Otherwise, I wouldn't keep repeating these things because they are pretty obvious, as I mentioned in the announcement. Okay. There are some rule of inference which have name, they are famous, like universal generalization. Like, for example, we have just for one arbitrary c inside this function, we can conclude that for all x's, it works. So you can also go through different ones to make yourself familiar with what are the rule of inference and sometimes we use it in the applications. Maybe you prefer to see the examples and remind yourself about the names of them, because we will keep repeating about the names anyways. So in next session, we will talk about proofs and theorems and why we need logic in order to use them inside a proof of our theorems. And that will make sense why we studied them. And it will start to make sense for you why we need it for computer science, hopefully in the next sessions, not for this week. Okay, guys, if you have any questions, please let me know. Otherwise, I will see you on Wednesdays. I'm about to read also what you have written during the time I was talking.